Okay, let's get started. Last session, we talked about the first paper that started it all, started the field of deep learning as we know it today. We talked a little bit about convolutions. We talked about the type of loss function that we're going to use and how to evaluate our models. There are some methods that I'm not covering from the paper. I will cover them in other papers through the means of studying other papers. For instance, they were using Dropout for the fully connected layers. And they were using activation functions like ReLU, rectified linear units. They were using data augmentation, which I didn't cover from the paper, but I will cover them through the means of other papers. Let's talk about Dropout first. So what is Dropout? There are two objectives when you do Dropout in deep learning. One is to prevent your models from overfitting. And what is overfitting? Overfitting happens when you are basically your model is too powerful that it's going to memorize your training data. So it's going to do a perfect job on your training data. But who cares about the training data? We want to take our algorithm, the one that comes out of deep learning, and put it into production. So our algorithm should be able to do a good job actually on the test data and actually in production. So if your model does a great job on your training data, but does very poorly on your test data, then that's called overfitting. And usually convolutional neural networks are less prone to overfitting because of the weight sharing idea. So you are sharing the same filter, which is, for instance, 3 by 3 or 11 by 11, and you're sliding it over your image. Because of the weight sharing idea, those are less prone to overfitting. But the densely connected ones, the ones that you usually put at the end of your neural network to extract your features, those are prone to overfitting. So Dropout is going to take care of that. Another objective is to combine multiple models together in a smart way. So usually when people report their accuracy or their evaluation metric, they usually combine multiple models together. They have an ensemble of models. So ensembling is a great idea for your model to be able to generalize to your test data and actually in production. The idea is that you're gonna have multiple models, maybe thousands of models, do the same task, and then they are gonna vote. Is this image a cat? Is this image a dog? And then the consensus is gonna be the output of the ensemble model. So Dropout is a way of ensembling in a smart way. We're gonna see why it is smart. So you have two objectives when you do Dropout. The network on the left is a standard neural network. These are the inputs and these are the neurons. So the input could be that particular portion of the image that you have, or it could be the dimensions. So think of these as input dimensions. And the neuron is gonna be the output of multiplying a bunch of weights by your input dimensions, adding them up, basically it's a dot product, and then putting the output here after pushing it through a nonlinearity. So this is gonna give you a neuron. That's gonna give you another neuron, and so on. And they have different weights, as you can see. Okay, that's how to visualize a neural net. What Dropout does is gonna drop some of your inputs, and it's gonna drop at random some of the neurons. It means that now you have less weights to do your summation on. What is the idea? The idea is that a single neuron should be able to do its job as independently as possible. This is what people call co-adaptation. You don't want your neurons to co-adapt. You don't want them, you want them to be independent, as independent as possible. So that's why it's gonna help with overfitting. The other aspect was ensembling. Each one of these guys is gonna be a neural net on its own with less weights and biases. So it has much fewer weights and biases and less neurons. It's definitely a weaker neural network compared to the one on the left. But at each iteration, you're gonna kill some of these neurons at random. So you have thousands of or millions of these small neural networks that are being trained at the same time. And now you need to form your ensemble in the end. And how are we going to do that is coming up. So there are two objectives. One is preventing overfitting. In that sense, it's just a regularization technique. The other one is you want to combine exponentially many different neural nets. And these are the type of the neural net architectures that you're combining.
Can I ask a quick question?
Sure.
So when you say like these are, if you're viewing each neuron as sort of an independent neural network, you mean that in the sense that each is its own model with many different layer types and its like own sort of structured neural network, not just like one sort of type of layer connected like over and over again, if that makes sense? Like it's not just one of these neurons. It's not like a single neuron is just only convolutional layers, and then another neuron is only like fully connected layers.
So what I'm talking about here in this slide is very generic. So it could be a convolutional neural net, it could be recurrent, it could be LSTM, it could be fully connected, it could be whatever.
Okay, and it could be any combination of any of those layer types in one model.
Yes, exactly.
Okay, cool, thank you.
But the idea is general.
Okay.
At some point in your training, you're gonna kill your neurons.
Okay.
Basically, per each data point that goes in, that data point is gonna see a different model.
Okay.
At random. So here is another way of looking at the same topic. So this neuron, for instance, this one, is gonna be present with probability P per each round of training. So each data point is gonna come in and it's either see this is either gonna see this neuron or is not gonna see this neuron. Basically, it's either gonna go through it or it's absent. It has to go through another route when you do your forward propagation. That's during training, but at testing, you don't want things to be random. You don't want to combine, you want to combine multiple neural network architectures together. And the way that the paper is doing it is keeping all of these neurons. So this neuron is gonna be always present. So all of the neurons are gonna be present in the end. But then you're gonna make your weights smaller by the same ratio, by the same probability ratio. It's sort of averaging. The question is applying dropout to a large neural network equivalent to the idea of ensembling? Yes, so it's equivalent to the idea of ensembling, but it's approximate ensembling. And the ensembling is happening here. When you're keeping all of your neurons, but then you are scaling down your weights by a probability. So it's the expectation of your neural network, but you're doing it in an approximate way. So it's approximate expected value of your neural network. So in the end, what you get is an ensemble. And as I said, the idea of a dropout is that each hidden unit, basically each one of these guys, has to be able to work independently. It shouldn't rely on the neural network, on the neuron next to it to do its job. Think of it this way. If I were to form a group in your class, in each session, I would randomly associate you with another team and team members. This way, you don't learn to rely on person X all the time to do your work. Or you do some of the work, the other person is going to do some other parts of the work, but you depend on each other. That's called co-adaptation. In our neural network, we don't want that to happen. During a single backpropagation pass, are the weights of the dropped neurons still updated, or they are excluded? So they are going to be excluded because they are absent. For that particular mini batch of data, they are absent. It means that their weights are going to be 0, and they are not going to get updated. Does that answer your question, John? Okay, perfect. So now let's get into the math. How do you actually write down the math, and how do you implement it? Let's say L denotes the number of hidden layers in your neural network. Basically, this is 1 layer, 2 layers, 3 layers. So that's L. And little l is gonna say, this is the first layer, this is the second layer, this is the third layer. That's the index of your layer. What you are seeing here, a neuron, is a nonlinearity applied on a hidden z. So that's YL. It's a nonlinearity applied on ZL. And what is ZL? It's a dot product between your weights and your inputs. So if these are your inputs and these are your weights, the arrows, you're multiplying them one by one and then adding them up together. That's going to give you a single number, and then you can add a scalar to it. That's your bias. That's going to be your neuron sitting here. That's the ith neuron, basically here. This is the first neuron, second neuron, third neuron, fourth neuron, fifth neuron. And L is going to be, in this case, 1. And that's what you're going to get. That's a typical neural network on the left. How do you do dropout? At layer L, you're going to sample from a Bernoulli distribution. Basically, you have a coin that you flip it, and then with probability P, it's going to be 1. With probability 1 minus P, it's going to be 0. That's your Bernoulli distribution, and they're independent. And at layer L, you get, for instance, 1, 2, 3, 4, 5 numbers. Some of them are 0, some of them are 1s. The idea is that you multiply your input by these random numbers. So it means that the neuron is going to be, some of them are going to be absent, some of them are going to be present. And that's going to give you y tilde L. The question is, how do you pick P? Usually a good number for P is 0.5. And for the intermediate layers, a good P is 0.5. Basically, half of the times you keep the neuron, half of the times you exclude it. And for the initial layer, a good one is probably 0.8, 0.85, 0.9. So it's not that sensitive to the choice of P. So that's why I'm saying a good number is usually 0.5. But the way that these are hyperparameters of your model, the way that you set them is usually using cross-validation. You take a look at your validation data and choose the best P that's giving you the least error or the most accurate model. So now that you killed some of your neurons and you kept other ones, the rest of it is the same as before. And because some of these guys are 0, we go back to your question, what happens in backpropagation? You are multiplying your weight by 0, so that weight doesn't exist. So in your backpropagation, that weight is not going to update because it is absent. For instance, this weight is absent, so it's not going to update. And the rest of it is just applying the nonlinearity. The question is, can you explain point 2 a bit more? And how this is accomplished by the dropout technique? So yes, that one we haven't yet covered. So Damien is asking about this part. How do you approximately combine exponentially many? I will explain that later. So far we are doing training, and each data point is going to see a new model when it goes through our neural network. So during training, each one of these guys learn to be independent or as independent as possible. Let's take a look at it visually. This is ZL before the activation. ZL is going to be a linear combination of 1 and your previous neurons coming from the previous layer. This is exactly what I'm writing here. And the 1 here stands for because you're multiplying B by a 1. So that's how you get your neuron. Ith neuron at layer L plus 1. That's your standard neural network. And visually, you're going to create some random numbers here. They are either 1 or 0, and you multiply it to get your y tildes. So that's how you kill your neurons. If this number is 0, y3 hat is going to be 0. It means that you're crossing it out. So it doesn't exist during training. The question is, how do you average it out? How do you average multiple neural networks out? You do it in expectation. And the way it happens is that half of the times, or P ratio of the times, P% of the times, some of the weights are present, and 1 minus P% of the time it's not present. The expected value is going to be P times the weight. During testing, you don't want things to be random, and that's how you do the averaging. And that's how I answer your question, Damien. This is how you combine exponentially many different neural network architectures. And you're doing it in an efficient way. And I'm going to show you empirically why this is efficient. There is another technique in the paper, and that's max norm normalization. It's basically weight clipping. You don't want your weight to become too big. That's another technique for regularizing neural networks. So I highly encourage you guys to read these two papers, especially the second one. There is a nice, I would say, there's a nice page in the paper that tells you how dropout, when you apply it to linear regression, is going to be equivalent to ridge regression. And ridge regression is basically regularizing your weights by its L2 norm. So it's actually doing a regularization for us. And that's why it prevents overfitting. So they apply the method, dropout, to multiple types of neural networks and in different domains. For instance, they apply it in vision, which is the topic of our course so far. They apply it to speech, text, and genetics. That's why I mentioned that these types of methods are universal. You can apply it to any type of neural network that you have. And these are different data sets. MNIST is the digits data set. Street view house numbers are the numbers that are coming from Google taking images, Google Earth. CFAR 10 and CFAR 100. These are low resolution images, and they have 10 labels and 100 labels, respectively. There is ImageNet, which is a huge data set, and the resolution is bigger. It's 256 by 256. There is TIMIT. It's a data set for speech. And Reuters is a data set for text, and the other one is for genetics. This is the size of the training data. This is the size of the test data. And they apply the method on all of these. And as you can see, some of these data sets are really small compared to 1.5 million, 1.2 million. These are small data sets. So it's very important for us to regularize our method. Otherwise, neural networks are going to overfit. And this is what you get. This is the classification error. The classification error during training for different types of models is going to end up being a better number, and it's going to converge faster with dropout compared to without dropout. So it's a very effective way of regularizing your models. And it's a huge gain.
Is there ever a reason not to use dropout?
Sometimes you want to take derivatives of your neural network with respect to inputs. Then dropout is going to mess up with those derivatives. But other than that, I would say, no, it's a good idea to use it all the time. Is there an advantage of starting with a higher number of neurons and using dropout versus a lower number of neurons? That's a good question. I would say the advantage is going to be the second point here. Your question is, yes, sort of addressing problem one. Maybe a smaller model is going to not overfit with a lower number of neurons. Probably it's going to be less prone to overfitting. But then you are not combining many different models if you use a single model with a smaller number of neurons. The question is, how are you approximately combining many different models? One way of combining it was during testing, per each data point, you look at a random model, take a look at the predictions, then get another data set, get another data point, push it through another random model. That's going to give you another prediction, and keep doing that for, I don't know, maybe 10 times, and then average the output. And then your test classification error on the average is going to be this number. And this is basically a Monte Carlo model averaging. Rather than doing this, we are just Monte Carlo averaging our outputs, our predictions. And yes, if you do it enough times, maybe 120 times, you might get a better model compared to the average weight scaling, because this line is weight scaling. But as you can see, this is within the margin of error. So this is actually a very good way of averaging neural networks in the end. You keep all of your weights, but then you scale them down with your probability. Any questions?
I had a quick question. So when we're talking about dropout as a method for combining different models, we're saying that we have individual network models that internally may also use dropout. And then we're using dropout to combine these models into some like ensemble supermodel. Is that correct?
That's sort of correct, yes. So you start with a huge model that's capable of overfitting, but then you keep killing neurons. If you do that, that's going to give you multiple smaller networks. And during training, these guys have to do good jobs. These are smaller neural networks, and they're random. In the end, you average them this way. Does that answer your question?
Yeah, I guess I'm a little confused if we're saying that each neuron, inside of each neuron, we might have like 3 convolutional layers and like 2 dense layers.
No. Each neuron is this. Whatever you do, whether it's a convolution or anything,
Okay.
each neuron is a linear combination of the input to the neuron.
Okay, that makes sense to me. I guess I was just getting a little confused with the word model and
no, here
how
you
I
don't
was using
a
it.
model. It's just this is just a neuron.
Okay.
And mathematically, this is what it is.
Yeah.
That is exactly what it is. So there is no other way of interpreting it. That's the interpretation. This is not a recurrent neural network. This is not a convolution. This is just linear combinations of your inputs. That's a bias. So there is a question. My understanding is that applying dropout inherently creates lots of models because they are not the same, since each of them have randomly dropped neurons. Exactly. So that's a correct interpretation. So any other questions, feedback? Do you have to maintain independence between neurons, or does dropout prevent co-adaptation due to dropped neurons? So dropout is actually gonna prevent co-adaptation. So it's gonna maintain independence for us. And as you can see, the title of the paper is Improving Neural Networks by Preventing Co-adaptation of Feature Detectors. So that's exactly what it's doing. Does that answer your question? Perfect. Any other questions? Is there a way to reproduce neural networks trained using Dropout? Is there a way to measure co-adaptation quantitatively? I'm going to answer John's question first. I'm not sure. Probably you can take a look at one of the neurons and see how it behaves during training with dropout versus without dropout. And now let's go back to Parker's question. Is there a way to reproduce neural networks trained using dropout? I don't know what you mean by reproduce.
Okay, I'll expand on that. So let's say I'm using Dropout. I'm randomly killing off neurons to create a model, and I'm happy with that model. But now somebody else wants to take the data set that I started with and reproduce that model. So is there a way, since Dropout is a random process, is there a way to reproduce that process
So there are
using
two
like a
aspects.
random generator seed?
Now I see what you're saying. So there are two things that are happening here. One is during training, things are random. You are correct. But during testing, it's when you want to give your model to somebody else, things are deterministic. So you keep all of the parameters, but then you weight them by the probability.
Okay.
So the model that you share with others and you put in production is this. After the training is done, this is what you share with others.
Okay. So I would share my weights and the probability that I chose.
Exactly.
Okay. Thank you.
So no, during testing, things are not random. They're deterministic. For how many iterations do you train a certain dropout network before moving to another? Every single data point that goes in your model is gonna see a random net. So every time you push a data point inside your neural network, a random number is gonna generate. And then a random set of your neurons are gonna be dropped out of your neural network. So what I want you to take home from this slide are the 2 points that I started with. Many people think of dropout as a regularization technique, and they don't know about the second point, that you're actually approximately combining exponentially many different neural networks together. And the key point is here. And many of you were asking questions whether this is actually deterministic or no. Is it a stochastic neural net? No. In the end, what you're gonna get is an averaged out neural network. So that one is gonna be deterministic. So if there are no other questions, I will move on to the next slide.